Every spacecraft we have ever launched is moving too slowly to reach the nearest star in any human lifetime. Every one. Voyager 1, our fastest outbound probe, would take 73,000 years to reach Alpha Centauri. Yet the universe has been traveling faster than light since the first moment it existed, and now physicists have published frameworks for drives that exploit that same loophole. If you subscribe and stay with us, we are going to walk through the loose cable that almost overturned Einstein, the accidental warp bubble discovered inside a power generation experiment. The peer review is legitimate. The implications for causality and the future of everything are real. Prepare yourselves. We begin. Picture the night sky on a clear evening far from any city. You can see thousands of stars, and every one of them feels close enough to matter, close enough to imagine reaching. That feeling is a beautiful, persistent lie. The nearest star system beyond our own is Alpha Centauri, sitting at 4.37 light-years away. That number sounds manageable until you translate it into something your body understands. Light, moving at just under 186,000 miles per second, takes 4.37 years to cover that distance. You are not made of light. Nothing we have ever launched into space comes anywhere close. Voyager 1 is our farthest traveling spacecraft. It is a confirmed fact that it moves at roughly 37,000 miles per hour, a speed that felt staggering when we launched it in 1977, and still feels impressive when you compare it to anything humans drive or fly. Compare it to light, though, and the number collapses into something almost tragic. At Voyager 1's speed, reaching the Alpha Centauri system would take approximately 73,000 years. Pause on that. Agriculture is only about 12,000 years old. Every civilization you have ever studied, every language developed, every empire risen and fallen, every written record in every archive on the planet, all of it fits inside a span of time that is not even a fifth of the journey to the nearest other star. Here is the part that starts to feel personally relevant. Every science fiction story you absorbed growing up, every narrative about humans spreading across the galaxy, making contact with other civilizations, or simply going to look at what is out there, rests quietly on the assumption that someone, somewhere, figured out how to close this gap. The gap is not a background detail. It is the entire problem. For most of the 20th century, the scientific consensus was essentially this: the gap is permanent. Physics says so. Einstein says so. The math is clear and final, and the stars will remain unreachable for any human timescale. But physics has a specific habit of looking final right before something important cracks. The same community that once insisted the atom was indivisible later split it. The community that swore the universe was static watched Edwin Hubble show it expanding. The community that said nothing could exceed the speed of sound broke that barrier in 1947. Each of those walls felt as absolute as this one, right up until the moment it did not. The speed of light deserves a closer, more careful examination because some of the most rigorous, peer-reviewed science of the last 5 years is quietly changing the shape of that wall in ways that would have seemed impossible to say out loud in a physics department just a decade ago. The question researchers are now asking is no longer whether faster-than-light travel is theoretically conceivable in principle. It is what kind of space-time geometry could allow it, how much energy it would require, and what we would need to understand about the fabric of reality to close even the first fraction of that 52 order of magnitude engineering gap. That shift from pure impossibility to an impossibly hard engineering problem with a measurable distance to close is the most significant change in this field in decades. Understanding why it happened means going back to what Einstein actually said, what he actually proved, and where, without any contradiction or hand-waving, the universe has been proving him incomplete all along. Einstein's speed limit sounds, on the surface, like a rule in the way that highway speed limits are rules. Something imposed, something that could theoretically be lifted with the right authority or the right machine. That framing is fundamentally wrong, and understanding exactly how wrong it is turns out to matter enormously. The limit encoded in special relativity is not an imposed constraint that physics decided to enforce. It emerges from the mathematics of how energy, mass, and velocity relate to each other, and what it implies is not that faster-than-light travel is against some cosmic regulation. It implies that faster-than-light travel for any object with mass is physically incoherent in a very specific and unforgiving way. Here is the confirmed fact at the core of it. As any massive object accelerates, it requires energy to push it faster. As its velocity approaches the speed of light, the energy required does not grow steeply but smoothly. It curves upward toward a vertical asymptote. At exactly light speed, the energy required becomes infinite. There is no power source in the observable universe sufficient for infinite energy. There is no engineering workaround. The requirement itself becomes the barrier, and the barrier thickens the closer you push toward it. A useful way to feel this concretely is to work through ordinary speeds first. Accelerating a car from 0 to 60 miles per hour requires a certain amount of fuel. Reaching 120 miles per hour from rest requires roughly 4 times as much, because kinetic energy scales with velocity squared, not linearly. Now extend that progression all the way upward. At 90% of the speed of light, the energy required to keep accelerating is already more than twice what Newtonian mechanics would predict. At 99% of light speed, the factor exceeds 7. At 99.9%, it climbs past 22. The numbers stack exponentially. As you approach a vertical line the mathematics will not allow you to cross. The phenomenon is not a theoretical extrapolation that physicists are still debating in the margins of journals. It is experimentally confirmed, repeatedly and precisely, in particle accelerators around the world. The Large Hadron Collider accelerates protons to within a vanishingly small fraction of the speed of light. Those protons gain effective mass as they accelerate. They require exponentially more energy per unit of additional speed gained. The equations of special relativity predict this behavior exactly, and the measurements confirm it exactly every single time for every particle at every energy level tested. Confirmed fact, verified in laboratories on 4 continents over more than half a century. What this means for human ambition is stark and specific. The obstacle standing between us and Alpha Centauri in any useful time frame is not a lack of sufficiently powerful engines or a shortage of political will to fund a mission. It is a law of nature that cannot be circumvented by better fuel, more advanced engineering, or longer development timelines within the framework of special relativity. To get around it, you would need to step outside that framework entirely. You would need a loophole in the underlying structure of physics itself. And the most extraordinary development in recent decades is that a loophole may genuinely exist, hidden inside a different set of Einstein's own equations, the deeper ones he published in 1915. The mind that built the wall may have left a door in the architecture, and recognizing it requires understanding what kind of speed limit was actually imposed, and what, deliberately or not, it left completely uncovered. Here is what nobody in a standard physics class ever gets told clearly enough. The famous rule that nothing can travel faster than light is demonstrably, continuously, and observationally false. Right now, at this exact moment, thousands of galaxies beyond a certain distance are receding from us faster than the speed of light. This is confirmed fact, fully consistent with our best cosmological models, and entirely uncontroversial among working astrophysicists. The universe has been performing faster-than-light motion at an enormous scale since long before any life existed on this planet, and it has never stopped. The apparent contradiction dissolves once you understand what the speed limit actually covers and, more critically, what it does not. Special relativity restricts the motion of objects moving through space. It says nothing, not a single equation, about the behavior of space itself. General relativity, Einstein's deeper theory of gravity and the geometry of spacetime describes how the fabric of space can stretch, curve, and expand. That fabric carries no speed restriction whatsoever. When distant galaxies recede from us faster than light, they are not moving through space at those velocities. The space between us and them is expanding, carrying those galaxies along the way. A mark on the surface of an inflating balloon moves away from another mark, without either mark actually traveling across the surface. The Hubble radius, sitting at roughly 14 billion light-years from Earth, is the boundary where the recession velocity of space equals the speed of light. Beyond that boundary, confirmed by observation, every galaxy is receding faster than light. Millions of galaxies. Billions, likely. The light from many of them will never reach us, because the space between us expands faster than light can cross it. General relativity predicted this consequence. Observation confirmed it. The universe has been exceeding the local speed limit since the Big Bang, using a mechanism that special relativity never prohibited because special relativity never governed the geometry of space itself. This distinction matters enormously for everything that follows in this story. Because if the faster-than-light prohibition were truly absolute in a universal sense, the universe would have to honor it too. The universe does not. What physics forbids is locally faster-than-light motion, the kind where you pick up a physical object and hurl it past light speed through the undisturbed space immediately surrounding it. What physics permits, and what it has always permitted within general relativity, is the deliberate manipulation of space-time geometry itself. Bend the geometry cleverly enough, in the right shape and the right configuration, and the prohibition simply does not apply. Every serious warp drive proposal written since 1994 exploits exactly this distinction. You do not accelerate a ship to faster-than-light velocities. You reshape the space-time geometry around it. The ship remains stationary within its local pocket of flat, undisturbed space. The geometry does the moving. Light is still the fastest thing traveling through the interior of the bubble. But the bubble, and everything riding inside it, arrives at a distant destination faster than light crossing the same distance through ordinary, unwarped space ever could. The universe has been demonstrating this principle since the beginning of time at the largest possible scale. The question now is whether physics that the universe applies unconsciously across billions of light-years can be reproduced deliberately at the scale of a spacecraft by beings who have understood the principle for only 30 years. The universe's record for fast expansion was set before anything in it had time to exist. In the first 10 to the minus 32nd seconds after the Big Bang, during the period cosmologists call cosmic inflation, space expanded by a factor of at least 10 to the 26th. Write that out and look at it. The number 1 followed by 26 zeros. A region of space smaller than a single proton became a volume roughly the size of a grapefruit in a moment so brief that no clock ever designed could measure it. Every analogy available to the human mind collapses at this point, because every analogy involves objects moving through space, and this was space itself, stretching in a way that had no physical object doing the moving, and no direction it was moving toward. This is confirmed fact, established through multiple independent lines of evidence that converge on the same conclusion. The cosmic microwave background radiation, the diffuse afterglow of the early universe that permeates all of space, has a temperature uniformity that defies any explanation other than inflation. Regions of the sky separated by distances that light could never have crossed in the universe's entire history since the Big Bang nevertheless have almost identical temperatures, differing by less than 1 part in 100,000. The only explanation that works is that those regions were once in contact, then pulled apart by inflation before light had time to traverse the growing gap. The large-scale structure of galaxies, sheets and filaments and voids spread across hundreds of millions of light-years also matches precisely the pattern that quantum fluctuations stretched by inflation would produce. Multiple lines of confirmed evidence point the same direction. The rate of that expansion was so far beyond the speed of light that describing it in miles per second becomes completely meaningless as a frame of reference. Inflation is described in terms of the multiplicative factor by which the universe's size increased, because that framing at least produces a number the mind can hold, however imperfectly. And the critical point for this story is that the expansion was entirely permitted by the equations of general relativity. Nothing in the physics was violated. Spacetime geometry expanded. Physics raises no objection to that whatsoever. This is the loophole every warp drive researcher is trying to capture in a controlled, deliberately created form. Inflation itself was not controlled, not localized, not directed toward any destination by any intelligence. It was a property of the early universe operating at energies and scales that will never recur. But it proved, in the most definitive way possible, that general relativity contains the physical ingredients for faster-than-light effective motion. The task physicists have set themselves is determining whether those same ingredients can be assembled deliberately on a much smaller scale in a region of space rather than across the entire cosmos. The irony embedded in this problem has a real sting to it. Inflation created the universe's current architecture. It spread the matter of the early cosmos into the vast expanse of hundreds of billions of galaxies across tens of billions of light-years. It manufactured the very distances that make the stars feel permanently out of reach. The event that made faster-than-light travel a necessity was itself a form of faster-than-light space-time geometry. The universe ran the first warp drive in its opening instant. What humanity is reaching for now is the extraordinarily difficult, possibly generational attempt to run one deliberately. Dark energy is confirmed to exist. It makes up 68% of all energy in the observable universe. It is causing the expansion of the cosmos to accelerate with every passing moment. Scientists have known about it since 1998, and despite extraordinary effort from the world's best physicists across more than 2 decades, we have no satisfying explanation of what it actually is, where it comes from, or how it operates at a fundamental level. That is the honest, current, peer-reviewed state of knowledge. The dominant component of the universe's energy budget is completely unexplained. The discovery arrived in 1998, and it arrived as a genuine shock. 2 independent research teams were using Type Ia supernovae, stellar explosions of consistent and predictable brightness that serve as cosmic distance markers, to measure how quickly gravity was slowing the universe's expansion over time. Saul Perlmutter led one group, Brian Schmidt and Adam Rees led the other, both expected to find deceleration. More mass in the universe means more gravitational pull across cosmic distances, and gravitational pull produces deceleration. Both teams expected to measure how much the expansion had been slowing and use that figure to calculate the universe's total mass. What they found instead was that the expansion had not slowed. It had accelerated. Something was pushing the cosmos apart, winning against gravity at every scale they could measure, and neither team had the faintest idea what it was. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for the discovery. The confirmed fact of accelerating expansion rewrote cosmology at its foundations. Einstein had introduced a cosmological constant in 1917, a term he added to his field equations to counteract gravity and prevent his model of the universe from predicting a collapse. When Edwin Hubble proved in 1929 that the universe was actively expanding, Einstein discarded the constant and reportedly described it as his greatest blunder. In 1998, it was quietly reinstated as the best mathematical stand-in available for whatever dark energy turns out to be. The constant fits the observations. What it represents physically is a mystery. The connection to faster-than-light travel is direct. Dark energy is the universe's own continuously operating faster-than-light mechanism. It drives the recession of the most distant galaxies past the light speed threshold and ensures the observable universe is slowly contracting from our perspective as region after region accelerates beyond permanent reach. The vacuum energy, predicted by quantum field theory, which should in principle correspond to dark energy, is between 10 to the 50th and 10 to the 120th times larger than the value we actually observe. This discrepancy has been called the worst theoretical prediction in the history of physics. It is not a rounding error. It is a symptom of fundamental incompatibility between our two most successful physical theories, and it sits exactly at the intersection of spacetime, geometry, and quantum vacuum properties that every warp drive proposal must ultimately navigate. Whatever dark energy is, understanding it even partially would change this entire field overnight. The stakes this creates extend beyond philosophical curiosity. The same incompatibility that makes dark energy unexplained is the gap that every space-time engineering proposal must eventually bridge. Whether dark energy represents a fixed property of empty space or a dynamic field that changes over time, changes everything about what might be possible. A dynamic field could in principle be locally altered. Determining which of these two descriptions is correct is one of the central open questions in observational cosmology, and the answer will shape the fundamental feasibility of every approach to faster-than-light space-time manipulation currently under investigation. September 23, 2011. The Oscillation Project with Emulsion Tracking Apparatus Collaboration at the Gran Sasso National Laboratory in Italy released a result that defied physics as it had been understood for more than a century. 174 scientists had signed the paper. The statistical confidence was 6 sigma, the threshold required for a formal discovery claim in particle physics, representing roughly a 1 in 500 million probability that the result was a random fluctuation. The claim, neutrinos fired from the European Organization for Nuclear Research in Geneva, had arrived at Gran Sasso 60.7 nanoseconds earlier than light would have taken to cover the same distance. Over a baseline of 730.534 kilometers, measured to within 10 centimeters, those particles had apparently traveled at 0.0025% above the speed of light. A nanosecond is 1 billionth of a second. 60.7 of them is, by any standard of ordinary daily experience, nothing at all. By the standards of precision measurement physics over a carefully determined baseline with 6 sigma confidence, it was one of the most significant numbers in the history of science. The team understood exactly what they were claiming. They had spent months running internal checks before releasing the result publicly. Roughly 30 of the collaboration's members refused to sign the paper because they were not satisfied, a detail that received far less attention than it deserved. 174 scientists did sign. The result went public, and the world responded in proportion to the magnitude of the claim. Headlines announced that Einstein had been overturned. Science journalists wrote careful pieces explaining that if the result withstood scrutiny, special relativity would require fundamental revision. Physicists who had built careers on the absoluteness of the light speed limit were called by reporters and asked whether they were simply wrong. Antonio Ereditato, the collaboration's spokesperson from the University of Bern, and Dario Ortiero, its physics coordinator, stood behind the result and publicly invited the broader community to help find any error if one existed. They stated confidence in their work. They had not, as it would turn out, checked everything. 5 months of global scientific discussion followed. Researchers at dozens of institutions ran independent analyses of the published data, hunting for the mistake. The atmosphere in the physics community was extraordinary, because 6 sigma results do not emerge from careless work. They require systematic, thorough, rigorous measurement that has been checked many times over. A 6 sigma result for a paradigm-shifting claim carries genuine weight, and almost everyone looking at the data assumed that something fundamental had either cracked or been mishandled at a level of sophistication no one had yet identified. What they were searching for was subtle. What they found was not subtle at all. The answer that would emerge would not change physics. It would change how every physicist felt about hardware checks forever after. The context that made the announcement so devastating was not merely the confidence of the claim. By 2011, the physics community had recovered considerable institutional credibility after decades of demanding extraordinary evidence for extraordinary results. A Six Sigma result from a multinational collaboration with properly documented methodology was precisely the kind of evidence that was supposed to change the conversation permanently. The world was primed to receive it. The fact that it collapsed over a cable was not just an embarrassment. It was a demonstration of how dramatically the instinct to believe a result can outrun the technical process of verifying it at every level, including the hardware. The error was a cable. One fiber optic cable connecting the Global Positioning System receiver to the master clock at the Gran Sasso facility had not been fully seated in its connector. The connection was physically imperfect at the point of contact. That single hardware fault introduced a timing error of approximately 73 nanoseconds, causing the detection system to record neutrino arrivals as earlier than they actually were. A second, entirely separate hardware problem compounded matters. A crystal oscillator in the master clock was running slightly too fast, introducing an independent error of approximately 15 nanoseconds in the opposite direction. The loose cable made neutrinos appear early. The oscillator error partially corrected for that appearance in the wrong way. The net result of these two equipment failures, running simultaneously and in opposing directions, was a spurious discrepancy of roughly 60 nanoseconds in the neutrino arrival measurements. The anomaly the collaboration had announced was 60.7 nanoseconds. The two hardware errors, combined, accounted for it almost exactly. There were no faster-than-light neutrinos. There was no need to revise special relativity. 174 scientists, months of rigorous internal analysis, Six Sigma statistical confidence, global newspaper headlines, and the answer was a cable that was not fully plugged in. Antonio Ereditato and Dario Ortiero both resigned on March 30th, 2012, the day the internal inquiry formally confirmed the equipment failures. The same collaboration that had announced the potential overturning of a century of physics confirmed, with considerably less media attention, that the neutrinos had traveled at precisely the speed physics had always predicted. Confirmation arrived quickly from independent sources. The International Committee for Future Accelerators experiment, operating a liquid argon detector at the same Gran Sasso facility, remeasured neutrino velocity using 3 nanosecond beam pulses and found arrival times within 4 nanoseconds of the light speed prediction. The Large Volume Detector and the Bobrick-Martire experiment, both operating at Gran Sasso independently, confirmed the same result. At the Neutrino 2012 conference in Kyoto on June 8th, Sergio Bertolucci, the European Organization for Nuclear Research's research director, officially confirmed for the international physics community that the oscillation project with emulsion tracking apparatus result was entirely an equipment artifact. What the episode exposed about science was genuinely uncomfortable and has not been forgotten. The 30 scientists who refused to sign the original paper because they were not satisfied were ultimately correct. The institutional pressure to publish a result of that magnitude, before every possible source of hardware error had been physically inspected, pushed the collaboration toward an announcement it was not ready to defend. The gap between checking your equations thoroughly and checking every connector in your timing chain turned out to be the gap between a discovery and a debacle. Every serious faster-than-light claim made since 2012 carries the shadow of that loose cable. The speed of light survived. The field did not emerge unscathed, and that lesson has shaped how researchers communicate every extraordinary result that has come since. The lesson resonated far beyond particle physics. In medicine, climate research, and materials science, sophisticated statistical analysis can establish a result with high formal confidence while leaving unchecked. the physical premises on which the entire data collection process rested. The oscillation project with emulsion tracking apparatus case demonstrated that 6 sigma significance, the gold standard of discovery, can be generated by 2 simultaneous hardware faults if no one inspects the connectors. The standard was revised not in mathematical terms, but in procedural ones. Checking the equations is necessary but insufficient. Checking every cable and every timing source at every point in the signal chain is part of the measurement. 24 years before the oscillation project with emulsion tracking apparatus scandal, a physicist at Columbia University named Gerald Feinberg was approaching the faster-than-light question from an entirely different direction. Instead of trying to push ordinary matter past the light barrier from below, Feinberg asked whether particles that had always been moving faster than light might exist from the beginning, born beyond the boundary and permanently unable to slow below it, in the same way that ordinary matter can never accelerate above it. In 1967, he formalized this framework in a paper published in Physical Review, and he coined a name for these hypothetical particles by drawing from the Greek word for swift. He called them tachyons. The mathematics of tachyons produces something deeply strange. For any ordinary particle, mass is a real positive number, and its energy increases without limit as its velocity approaches the speed of light. For a tachyon to remain consistent with the equations while always traveling faster than light, the term representing mass squared must be negative. A negative mass squared means the mass itself is imaginary, in the precise, formal mathematical sense, involving the square root of a negative number. The tachyon would not merely exceed the speed limit. It would carry a property that has no equivalent in any observed or measured particle. Every concept of mass developed through a century of direct experimental observation would simply not apply. No tachyon has ever been detected, and the absence is not surprising. Because tachyons would always be moving faster than light, they could never slow to a velocity at which any detector built from ordinary matter could directly observe them. Their interactions with ordinary particles might leave indirect signatures, but the signatures would be subtle and ambiguous, easily attributed to other causes. Every dedicated search came up empty. The searches eventually became infrequent because the theoretical foundation for tachyons as real physical particles seemed increasingly weak, and the detection problem seemed permanently intractable. The deeper difficulty was not experimental but conceptual. Theory. If a tachyon can carry information, the mathematics of special relativity allows constructing scenarios, depending on the reference frame of the observer, where that information arrives before it was sent. Faster than light signaling and backward in time information transfer are, within special relativity, the same phenomenon viewed from different vantage points. Feinberg understood this and offered arguments for why paradoxes might be avoidable in practice. Most physicists found those arguments unconvincing. Tachyons spent the next 6 decades classified as mathematical curiosities rather than serious physics, present in the textbooks as a thought experiment and absent from experimental programs as a target. Then came July 2024. Physicists Andrzej Dragan from the University of Warsaw and Arthur Eckert from Oxford published a paper in Physical Review D, arguing that the causality objections that had closed the door on tachyons were based on incorrectly applied boundary conditions that had gone unchallenged for 60 years. The argument was mathematical, peer-reviewed, and specific. The door that physics had declared shut was quietly, carefully reopened, and the implications for what faster-than-light physics might permit are still being worked out. What Feinberg's mathematical framework ultimately revealed was that the universe's classification of particles may be more complex than ordinary experience suggests. The familiar inventory of the Standard Model is organized around mass being a real, positive quantity. Tachyons introduce a category that sits on the other side of a mathematical mirror, carrying a property that ordinary particles cannot have. Whether that mirror has anything on the far side that exists in nature, or whether it is purely a formal artifact, is the question that 60 years of physics attempted to answer by ruling it out, and which two researchers at leading institutions reopened in 2024 by challenging the ruling itself. The idea that would give the faster-than-light physics community its most durable mathematical framework arrived on a Friday evening in 1994 while a Mexican doctoral student was watching television. Miguel Alcubierre was completing his doctorate at the University of Wales, Cardiff, immersed in general relativity, and the program was Star Trek. An episode featured the starship's warp drive, described in the show as a propulsion system allowing travel between star systems in days. Alcubierre found himself asking not whether such a device was plausible as engineering, but whether the concept could be expressed mathematically within physics he already understood. What he worked out was that general relativity contains no prohibition against spacetime geometry changing in ways that carry enclosed objects from one location to another faster than light would take through undistorted space. The special relativity barrier applies to objects moving through space in the conventional sense. It says nothing about the space itself being reshaped around an object. You could write a mathematical description of spacetime, called a metric, in which space contracted in front of the ship and expanded behind it, while the ship sat stationary in a local region of undisturbed flat space. Locally, inside that region, nothing would exceed the speed of light. Globally, the ship would complete an interstellar journey faster than a light beam crossing the same route through ordinary flat space ever could, because the geometry itself had done the traveling. Alcubierre published in Classical and Quantum Gravity in 1994. The title stated the claim plainly: the warp drive, hyperfast travel within general relativity. The paper proved the metric was mathematically valid. It was a genuine proof of concept, the first rigorous demonstration that general relativity permits this class of geometry. The same paper also identified the fundamental catch with complete honesty. Sustaining the bubble required matter with negative energy density, a substance with properties unlike anything observed in nature at macroscopic scales, and something the universe does not demonstrably produce in useful quantities. The negative energy requirement emerged directly from the bubble stability mathematics. Ordinary matter curves spacetime toward attraction and compression. The warp metric requires spacetime to curve in the opposing direction in specific regions, contracting the front and expanding the rear of the bubble. That requires matter with precisely opposing energy properties. Alcubierre acknowledged this openly. He described the paper as a proof of concept rather than an engineering proposal, and later admitted the drive was almost certainly unbuildable in the form he had described. What the paper established, rigorously and permanently, was that general relativity does not forbid warp geometry. The equations permit it. The obstacle was not theoretical impossibility but extreme physical resource requirements, and in the history of physics, resource problems have a track record of eventually yielding to researchers who find a fundamentally different approach. The 30-year search for that different approach, and what it found, is where this story was always heading. The personal dimension of Alcubierre's story carries a lesson that the technical literature does not highlight but which matters for understanding how science actually moves. He was a doctoral student, not a senior researcher with dedicated laboratory funding. He wrote the paper in his own time, motivated by curiosity about whether the fiction he watched for entertainment had any underlying mathematical coherence. The willingness to ask the question that professional reputation might counsel against pursuing is precisely why the paper exists at all. What established consensus dismissed as fantasy, a student asked whether it could be expressed in confirmed physics, and the answer changed the field permanently. The Alcubierre warp drive gave theoretical physics something it had lacked since Einstein closed the door on faster-than-light travel: a rigorous mathematical framework for discussing the problem as a question of geometry and energy rather than pure prohibition. Researchers could now compute specific properties of the warp bubble, test stability, examine what the full equations implied about energy requirements, passenger conditions, and the relationship between the bubble geometry and the laws of causality. The theoretical toolbox existed and was peer-reviewed. The first serious calculations using that toolbox produced a number so large it felt less like an engineering constraint and more like the universe's way of saying it was not interested in negotiating. The original energy requirement for an Alcubierre bubble large enough to contain a spacecraft came out to approximately the mass of Jupiter, converted entirely into exotic negative energy matter. Jupiter is the solar system's largest planet, with a mass of roughly 1.9 times 10 to the 27th kilograms. The entire mass of that planet, converted into a form of matter never demonstrated to exist at any macroscopic scale, was what the warp geometry demanded. The number was so extreme that comparing it to any conventional energy source was meaningless. It was not a challenge for advanced engineering. It was a challenge for the existence of the required substance in the first place. The exotic matter problem had a second layer beyond sheer quantity. Negative energy density does exist in nature, at very small scales, as a confirmed experimental fact. The Casimir effect, the quantum phenomenon in which two uncharged parallel metal plates placed very close together in a vacuum experience an attractive force from quantum vacuum fluctuations, produces a thin region of negative energy density between the plates. Steve Lamoureux measured the Casimir force to 5% accuracy at Los Alamos National Laboratory in 1997. The measurement confirmed what the theory predicted. Negative energy density is real. It is measurable. It exists in the universe. But the amount the Casimir effect produces is approximately 10 to the minus 4 joules per cubic meter. A warp drive geometry operating at 200 times the speed of light requires approximately 10 to the 48th joules per cubic meter of negative energy. The gap between what nature produces naturally and what the warp drive needs is 52 orders of magnitude. To appreciate the size of that gap, the number of atoms in the observable universe is roughly 10 to the 80. 52 orders of magnitude is not a distance that engineering closes on any recognizable timeline. It requires either a fundamentally different warp geometry, an entirely new physical source of negative energy, or a reason to believe the original energy calculation was an artifact of the specific metric chosen, rather than a property of warp geometry in general. Harold White, working at the National Aeronautics and Space Administration's Eagle Works laboratories in Houston, believed in 2012 that he had found the third path. His announcement reduced the energy requirement from Jupiter's mass to approximately 700 kilograms, and the global press reported it as a breakthrough. Understanding what he claimed, why the physics community was not convinced, and what the attempt to solve the problem ultimately produced, is where this story finally begins to turn towards something new. The number 700 kilograms is seductive precisely because it sounds achievable. Harold White's 2012 announcement from the Eagle Works laboratories in Houston did not merely trim the margins of the energy problem that had stalled warp drive research for nearly 2 decades. He claimed to have transformed it entirely, to have changed the nature of the challenge rather than simply reduced its scale. Jupiter's mass worth of exotic matter reduced to the weight of a small automobile sitting in an ordinary driveway. The global press did not whisper this news. They broadcast it across every science publication and mainstream outlet that employed a physics writer, and several that did not. Journalists used phrases like breakthrough, feasible, and within reach. Television segments described a National Aeronautics and Space Administration engineer who had cracked a problem that paralyzed theoretical physics for 18 years, and for a brief, glittering stretch of weeks, it genuinely seemed as though the warp drive had graduated from speculative philosophy into practical engineering. The physics community responded with something quieter and considerably colder. The dispute was not about whether White's intentions were sound or his laboratory competent. The argument was narrower and more technical. It centered on whether the specific calculation that produced the 700 kilogram figure actually held together when other physicists tried to follow it. White had proposed a modification to the original bubble geometry. Instead of a thin shell surrounding the payload, he described a thicker, oscillating ring configuration, arguing this shape dramatically altered the total energy budget. What followed was not a published exchange of named arguments. It was a silence with edges. Other physicists attempted to reproduce the specific reduction. The figure of approximately 700 kilograms could not be independently verified. Technical objections appeared in the peer-reviewed literature, challenging whether the geometry White proposed was internally consistent with the underlying equations it claimed to exploit. This is confirmed as a matter of documented scientific dispute. The claim was not retracted because the author refused to retract it, but it was also not validated by the community that would need to build on it. That distinction carries real weight in how science progresses. There is a specific and measurable harm that premature headlines inflict on a research field. The public absorbs the announcement and forgets the correction. The breakthrough calcifies in popular understanding while the working researchers quietly catalogue the disputed result as unresolved and move forward. By approximately 2015, most physicists engaged with warp geometry had set White's energy optimization to the side as an unconfirmed claim rather than a settled advance. The problem of energy cost had not been solved. It had been restated in terms of assumptions that no independent reviewer could verify from the published derivation. And yet Harold White kept working. He did not abandon the field when the excitement faded and the technical objections accumulated. He changed institutions, shifted focus toward quantum vacuum research, and continued pressing on questions of whether confined vacuum geometry could be experimentally controlled and theoretically understood. The answer he eventually found in 2021 was not the one he had been pursuing in 2012. But the fact that he remained in the problem is part of the reason that answer came when it did. The celebration had been premature by at least 9 years. Sometimes a claim made too early and too loudly is still pointing at a direction worth following all the way to the end. Gunter Nimtz was not a fringe scientist. He held a chair at the University of Cologne and later at the University of Koblenz-Landau, both legitimate institutions with established reputations in experimental physics. His laboratory was accredited, his equipment was properly calibrated and maintained, his experimental methodology was carefully documented. Other researchers who entered his laboratory and ran the same procedures obtained the same measured results. His experiments were reproducible. The extraordinary element was not the quality of his experimental practice. It was the interpretation he placed on the data his equipment returned, and the 15 years he spent insisting that interpretation was correct. The experimental setup involved microwave tunneling through a classically forbidden zone. A section of waveguide, machined to specific dimensions, blocks the passage of microwave signals at a given frequency, creating a region the classical physics of electromagnetic propagation says a signal cannot cross. Quantum mechanics permits a particle or field to traverse that forbidden zone through a process called quantum tunneling, appearing on the other side without having traveled through the middle in any continuous classical sense. Nimtz set out to measure the time required for this tunneling process to complete. His results, accumulated across experiments spanning from 1992 to 2007, consistently indicated that the transit time through the barrier was unmeasurably small, effectively instantaneous. The carrier emerged at the output before it had time to cross classically. He went further than reporting a null transit time, and this is where the story acquires its unusual texture. In 1994, Nimtz encoded Mozart's Symphony No. 40 onto a microwave carrier signal and transmitted it through the tunnel barrier. He measured the output signal at the far end. By his reckoning, the symphony had arrived at 4.7 times the speed of light, not marginally above the speed limit, not at a measurement excess that might dissolve under tighter experimental control. 4.7 times the maximum speed permitted by the entire framework of special relativity. transmitted on microwave wings through a laboratory cavity in Germany. He published the result, lectured internationally, and maintained the position with visible conviction for 15 years straight. Herbert Winful, at the University of Michigan, examined the claim with care and published his rebuttal across 2006 and 2007. The response was technically precise and, in the judgment of the broader physics community, definitive. What Lentz had measured was not the transit time of a photon traveling through the barrier at superluminal speed. He had measured the stored energy lifetime of the microwave cavity itself. The tunnel barrier does not transmit a signal that races across the forbidden zone faster than light. It accumulates energy in a resonant structure and then releases that energy in a pattern that mimics the shape of an early arrival. The apparent speed of transmission that Lentz recorded was a property of how the cavity stores and discharges energy over time, not evidence of any signal carrier exceeding the speed of light in transit. No information crossed the barrier faster than light. This is confirmed by the consensus of the physics community following Winful's publications. The stored energy lifetime had been mistaken for a propagation velocity. 15 years of certainty rested on measuring the wrong thing entirely. March of 2021 arrived without any particular signal that it would matter. The journals that publish research in general relativity and theoretical physics ran their normal submission cycles. No agency had scheduled a press event. No research institution issued a preview announcement. The physicists working on warp drive geometry during those weeks were not, for the most part, expecting anything that would require revising the field's foundational assumptions. And then, within roughly 30 days, 2 independent papers appeared in the same journal that together invalidated the central premise that had organized every serious warp drive publication since 1994. Erik Lentz was working across the Georg August Universität Göttingen and the Pacific Northwest National Laboratory. His paper, published in Classical and Quantum Gravity in March 2021, was titled Breaking the Warp Barrier: Hyperfast Solitons in Einstein-Maxwell Plasma Theory. The structures Lentz had identified were a class of solutions called solitons. A soliton is a self-reinforcing wave that maintains its shape as it propagates through a medium, resisting the dispersion that causes ordinary waves to spread and dissipate over distance. They exist as physical phenomena in ocean wave dynamics, in optical fiber communications, in plasma physics. Lentz showed they could also exist as stable self-reinforcing structures in the curvature of spacetime itself, propagating through the geometry of the universe rather than through any material medium. This is confirmed as a peer-reviewed theoretical result, not a physical demonstration. What it means requires a careful step. Every warp drive solution published in the 27 years following Alcubierre's original paper had, in one form or another, required negative energy density. Fields or distributions of matter with physical properties found nowhere in the experimentally confirmed inventory of the universe at macroscopic scales. Lentz's solitons required none of this. They satisfied the weak energy condition, the mathematical requirement that any observer measuring the local energy density of the space-time configuration would record a value of 0 or greater. His warp geometry was built entirely from positive energy, the kind that can be measured in a laboratory, the kind that exists. The energy cost was not small. Lentz acknowledged directly that a bubble 100 meters in radius, traveling at the speed of light, would require hundreds of times the mass of Jupiter in energy. That figure is not promising for any engineering project humans might contemplate with current or projected resources. But the fundamental category of the problem had changed. For 27 years, the question had been whether exotic matter could be obtained in sufficient quantities. After March 2021, the question became whether an enormous positive energy budget could be reduced through improved geometric understanding and new physics. Those are different problems in a meaningful way. The first may have no answer available to us. The second has a direction. A direction is a place to work. What makes Lentz's approach significant beyond the energy condition result is the class of structure it uses. Solitons are not exotic. They appear in well-understood natural systems where wave propagation and medium response interact in a particular balance. That a soliton structure can exist in spacetime geometry rather than in a material medium was not mathematically surprising in retrospect, given the similarities between the governing equations. But no one had looked for it. The tool existed in a different field. The researcher who found it was working across a physics laboratory and a mathematics department simultaneously, drawing on a broader toolkit than any specialist in either field alone would typically carry. Alexei Bobrick and Casimir-Martire were not coordinating with Lentz. They were not collaborating on a joint effort to rewrite the energy conditions of warp drive physics. They were working in parallel on a different approach, and their paper arrived in the same journal in the same month through independent development. The title was Introducing Physical Warp Drives, published in Classical and Quantum Gravity in March 2021, Volume 38, Number 10. The word introducing was carrying more weight than it might appear to. What they were introducing was not a single new solution. They were introducing a framework, a comprehensive system of classification that could hold all possible warp drive geometries within a single structured account. Before this paper, warp drive research was organized around specific solutions, examined one at a time. A physicist studied the Alcubierre metric, or one of its established geometric variants, or proposed a new configuration and checked its properties against the known constraints. The field had accumulated individual solutions over nearly 3 decades like specimens in separate jars, each examined on its own terms, with no map showing how they related to each other as members of larger mathematical families. What it lacked was what every maturing scientific discipline eventually requires: a taxonomy, a classification system that organizes the space of possibilities rather than listing instances of them. Bobrick and Martire built that taxonomy. Their classification demonstrated, among other results, that an entire family of subluminal warp drives can be powered by purely positive energy. Subluminal here carries a specific technical meaning. The drive moves a payload faster than light would travel the same route through undistorted spacetime, while remaining locally subluminal inside the bubble. These configurations require no exotic matter. They are, by the confirmed framework, physically permissible in a universe that contains only the matter and energy we know to exist. The paper has been cited more than 60 times by researchers working across 4 continents, which for a theoretical physics paper in this specialized area is a meaningful measure of its reception. The energy costs in the positive energy subluminal family remain substantial. Several Jupiter masses worth of energy, even for a small bubble. But the classification had accomplished something that energy reduction alone could not. It had given warp drive physics the architecture of a genuine science. A field organized into a taxonomy can be systematically improved. Researchers could now ask not only whether a given solution satisfied its own internal requirements, but where in the complete classification it sat, what constraints it inherited from its mathematical family, and what class of modification might move it toward the efficiency boundary. The field had acquired the internal structure that makes cumulative progress possible. The breadth of the international response offers evidence of how much the field had been waiting for exactly this structure. Researchers in Argentina, New Zealand, Canada, and multiple European countries were working on warp geometry problems that could not be fully communicated without a shared classificatory language. The paper gave them that language. The 60-plus citations accumulated within 3 years came from groups that were not simply extending the paper's own results, but using its framework to organize work they had already been doing independently. A taxonomy that arrives precisely when a maturing discipline needs it can accelerate integration in ways that are difficult to attribute to any single result. 27 years is a long time for a single unexamined assumption to define the outer boundary of what a field considers possible. The assumption that settled into place after Alcubierre's 1994 paper was stated cleanly and appeared to follow directly from the mathematics. Warp drives require exotic negative energy matter. The implication carried in that statement was broader than just a feature of one metric. It was treated as a fundamental constraint on the physics of superluminal spacetime transport generally. Researchers spent years working on how to reduce the required quantity of exotic matter, accepting its necessity as a fixed condition of the problem rather than a hypothesis to be tested against a wider class of solutions. The field was not being incautious. The Alcubierre metric and its close relatives all pointed in the same direction. From inside that family of solutions, the requirement for exotic matter appeared universal. The researchers who worked on this problem were following the evidence as it presented itself, and the evidence available from the solutions they could construct consistently demanded negative energy density. The assumption was a reasonable generalization from an incomplete sample. That is a different kind of error than carelessness, but it is still an error with consequences. The 2021 papers invalidated it through counterexample. Lentz's solitons existed in a region of solution space outside the Alcubierre family, and they satisfied energy conditions that the Alcubierre metric violates. Bobrick-Martire's classification showed that the Alcubierre metric occupied one corner of a much larger space of geometries, and other corners had categorically different energy properties. Two groups working independently arrived at the same invalidating conclusion from different mathematical entry points in the same month. 27 years of field-level consensus about a foundational constraint had rested on an incomplete map of the available solutions. This is confirmed as a matter of the published record in peer-reviewed literature. The implications, which remain theoretical, are significant for how the field now operates. If the most studied assumption in warp drive physics for nearly 3 decades turned out to be an artifact of examining only one family of solutions, then the question of what other assumptions in the field might be similarly bounded becomes impossible to ignore. Scientific progress inside a container does not tell you what exists outside it. Sometimes the most important advance is not a new answer, but the discovery that the container was never as large as the field believed. The historical parallel deserves emphasis. The periodic table did not discover new elements. It revealed the structure that made predicting undiscovered elements possible. In warp drive physics, the Bobrick-Martire classification did not solve the energy problem. It revealed the structure of the solution space, making it possible to ask which parts had not yet been explored, where the boundaries of the energy cost function lie, and what approaches might reach regions with fundamentally different properties. The field gained, in a single paper, the ability to formulate questions it previously lacked the vocabulary to ask. That is a different kind of progress from finding an answer, but it is the kind that precedes answers being found. Harold White had left the National Aeronautics and Space Administration and moved to the Limitless Space Institute by the time the discovery happened. The research he was conducting at the time was funded by the Defense Advanced Research Projects Agency. The subject was Casimir cavities, the physical structures in which quantum vacuum fluctuations produce measurable effects on energy density. White's team was working to understand whether specific geometric configurations of those cavities could amplify or direct the vacuum energy effects they produced. The work was technically demanding, experimentally grounded, and was not organized around warp drive physics. It was basic research into confined quantum vacuum behavior. The specific structure under analysis was extraordinarily small. A sphere approximately 1 micron in diameter, positioned inside a cylinder approximately 4 microns in diameter. White and his colleagues computed the energy density distribution produced by the quantum vacuum in and around that geometry. The output they obtained was not what the research program had been designed to find. The energy density distribution of that specific Casimir cavity configuration matched the geometry of the Alcubierre warp metric. The shape of the quantum vacuum energy around the physical structure, when expressed mathematically, mirrored the shape of the spacetime curvature that Alcubierre's equations describe for a warp bubble. White published this result in the European physical journal C in December 2021. This is confirmed as a peer-reviewed publication. No claim was made that actual space-time curvature was being induced or that any warp effect was physically present in the laboratory. The match was mathematical and geometric, not a measured physical distortion. What the result raised as a possibility was this: the universe, conducting the ordinary quantum vacuum experiments that physicists run in laboratories routinely around the world, may already be generating energy density distributions whose shape matches the geometry of warp spacetime, at scales far too small to affect any object larger than a single micron, at scales visible only in the equations of the vacuum. But the geometry was there, arising without any deliberate attempt to produce it, from physics that has been confirmed and studied for decades. What that means for the relationship between vacuum physics and warp geometry is, at this point in the story, a genuine open question. The confirmed fact is the match. The interpretation remains a mystery. The accidental character of White's discovery deserves careful attention. Accidental discoveries that redirect a research field typically share a feature. The researcher who encounters the unexpected result has enough background to recognize it as unexpected. White had spent years building expertise in the mathematical structure of the Alcubierre metric. When the energy density distribution from his cavity calculation emerged with a recognizable shape, that recognition was possible only because the prepared mind was present. The Defense Advanced Research Projects Agency had funded research into energy harvesting for small electronics, in effect, and received instead a connection between quantum vacuum engineering and warp drive geometry that no direct proposal would have been funded to investigate. The gap is 52 orders of magnitude. That phrase appears in the peer-reviewed literature, and it deserves to be held still for a moment rather than rushed through. An order of magnitude is a factor of 10. 52 orders of magnitude is 10 raised to the 52nd power. For comparison, the number of atoms estimated to exist in the entire observable universe is roughly 10 raised to the 80th power. The gap between what the Casimir effect can produce and what a warp drive requires is a factor of 10 to the 52nd. It is a number that has nearly the same number of digits as the count of every atom, in everything we can observe, in every direction, out to 14 billion light-years. The Casimir effect produces approximately 10 to the negative 4th joules of negative energy per cubic meter. Steve Lamoureux confirmed this at the Los Alamos National Laboratory in 1997 with a measurement accurate to 5%. That measurement is confirmed experimental fact, not estimate. A warp drive operating at 200 times the speed of light, calculated from the best available peer-reviewed framework, requires approximately 10 to the 48th joules of negative energy density per cubic meter. The 52 order gap between those numbers is the honest arithmetic of the situation. There is no engineering precedent in human history for closing a gap at this scale. Moving from the first powered flight at Kitty Hawk, North Carolina, to orbital spaceflight involved roughly 7 orders of magnitude improvement in speed. Moving from the first nuclear fission chain reaction to a functional thermonuclear weapon involved roughly 6 orders of magnitude in yield. Closing the gap between these two numbers would require advances that dwarf every engineering achievement in the history of human civilization stacked together. The 52 order gap does not close on any human timescale, using any known physical process. And yet the number is finite. That is the only honest statement physics can currently offer. The gap is real, its scale is staggering, and the direction toward narrowing it points toward understanding how vacuum geometry can be controlled at quantum scales. Whether negative energy density sources beyond the Casimir effect can be engineered or identified in nature, and whether the soliton and classification results from 2021 point toward geometric configurations that reduced the requirements substantially. Lentz himself stated that a 30-order reduction in energy requirements would be necessary for practical consideration. 22 additional orders would still remain after that. No one working in this field pretends otherwise. The math works. The abyss between the math and any physical realization is the largest engineering gap humanity has ever named. What keeps this gap from being purely discouraging is the history of what preceded other large-scale engineering challenges in physics. The first calculation of nuclear yield was accurate to within factors that would have seemed inadequate for any precision application. The actual engineering reduced the theoretical threshold not by improving the original calculation incrementally, but by discovering new physical phenomena that the original calculation had not included. The 52-order gap in warp drive energy requirements may represent the distance between the first calculation and the calculation that uses all the relevant physics, rather than the distance between current capabilities and a fixed and permanent destination. In 2024, Applied Physics, the company co-founded by Casimir-Martire, released an open-source software package called Warp Factory. The program was built as a numerical solver for arbitrary warp drive metrics. A researcher anywhere in the world could take a proposed space-time geometry, run it through the solver, and receive a computed output showing whether the geometry satisfied the relevant energy conditions, what the energy cost of the configuration was, and how it compared numerically to other known solutions. Before this tool existed, testing a new warp metric required either building specialized computational infrastructure within an institutional setting or working through the mathematics by hand, both of which imposed significant barriers to entry for researchers without major institutional support. Applied Physics also announced the Warp Fund simultaneously with the software release, $500,000 designated for researchers pursuing serious experimental and theoretical work on physical warp drive problems. The combination was a deliberate strategic choice. If the bottleneck in the field was the absence of shared computational infrastructure rather than the absence of theoretical imagination, then releasing the tools to the broader research community would generate more progress than concentrating the same resources within a single group. The observable effect within the first year was real. Researchers working across multiple continents were running proposed geometries through Warp Factory and publishing comparative results. Groups based in Canada, Argentina, European research centers, and New Zealand contributed solutions that could now be evaluated against a common computational standard. Papers began presenting energy efficiency ratings generated by the shared tool, and the language of comparison in the field shifted. Researchers were no longer arguing only about whether a proposed solution was internally consistent. They were arguing about measured performance differences across a shared evaluation framework. The field was acquiring the shared vocabulary and comparable measurement infrastructure that reproducible engineering disciplines depend on. The 52-order energy gap had not changed. The number of researchers equipped to work systematically against it from different geometric directions, using tools that produced directly comparable outputs, had grown in a way that prior decades of the field had not seen. Science that can be distributed is science that can be accelerated. The open-source release of Warp Factory had a secondary effect beyond accelerating research output. It changed the character of what gets published. Before shared computational tools existed, warp drive papers focused on a single proposed geometry analyzed in depth. With a common solver available, papers began presenting comparative studies of multiple geometries evaluated against shared metrics, making the relative merits of different approaches legible for the first time. The field began to look less like a collection of competing proposals and more like a systematic search through a defined space of options, which is precisely what any engineering discipline requires before any single option can be seriously prioritized for development. The collaborative effect had another dimension. As more research groups began publishing results calibrated against shared energy condition metrics, The implicit peer review process across the field became more transparent. A result that claimed significant improvement over prior work could now be checked against a common baseline by anyone with access to the software. Claims that had previously required trusting the author's own comparative analysis became independently verifiable. The combination of open tools, shared metrics, and distributed research capacity changed the field's internal accountability structure in ways that prior decades of isolated individual research programs had not achieved. One assumption had persisted beneath nearly every discussion of warp drive detectability since the field began taking the physics seriously. The assumption was stated plainly: warp drives cannot be experimentally observed using instruments we currently possess, because any warp drive operating somewhere in our galaxy would produce space-time effects too small, too distant, or too causally isolated from the surrounding environment to register on any detector we have built or are planning to build. If an advanced civilization in our region of the galaxy had solved the energy problem and was actively using warp technology, physics offered no observational path to knowing that. The universe would look identical regardless. This assumption went largely unchallenged for decades because it appeared to follow straightforwardly from the scale of the effects involved. In 2024, Katie Clough and colleagues at Queen Mary University London published a paper in the Open Journal of Astrophysics that replaced that assumption with a specific, testable, quantified alternative. The paper did not address the detectability of a warp bubble in operation. It addressed what happens when a warp bubble collapses. When the space-time curvature of a warp geometry is shut down, the rapid relaxation of the metric produces a burst of gravitational radiation. The frequency profile of that burst, the way its amplitude decays over time, and the specific pattern it leaves in a gravitational wave detector are calculably distinct from the gravitational wave signatures produced by compact object mergers, stellar collapses, and other confirmed gravitational wave sources already being catalogued. Clough's team calculated that a warp bubble of physically reasonable dimensions collapsing at a physically reasonable rate would produce a signal within the detection sensitivity of laser interferometer gravitational wave, observatory-class instruments. This is confirmed as a theoretical result in a peer-reviewed publication. The implication it carries requires care. We still cannot detect a warp bubble in operation. We potentially can detect the gravitational wave signature of one that has been turned off. Every warp experiment that has ever been conducted, if any have occurred anywhere in our observable region of the universe since gravitational wave detectors began operating, would have produced a specific detectable signal at shutdown. Whether any such signals exist in archived gravitational wave data, unrecognized because no one yet knew what pattern to look for, is an open empirical question that previous physics would not have known how to ask. The potential to search archived gravitational wave data for warp signatures is not a distant future project. It is something that could, in principle, be done with currently existing data from detectors that have been running since 2015. Every event catalogued has been classified against known signatures of confirmed astrophysical processes. Warp bubble collapse signatures were not part of that classification scheme because the mathematics to calculate them did not exist until 2024. A targeted search using the published waveform templates could now be applied to the archive. Whether anyone will conduct that search and what they might find remains an open empirical question that previous physics would not have known how to frame. The paper appeared in Classical and Quantum Gravity in December 2025. Harold White was the lead author. The institution listed was Casimir Space, which White had co-founded after departing the Limitless Space Institute. The subject of the paper was a new warp drive topology, a specific geometric arrangement of the field-generating components around a central payload region, derived from working through the energy distribution requirements of a particular class of warp metric the team had been developing. The topology was not chosen for visual appeal or for any reason external to the physics. It emerged from the equations, The configuration required twin nacelles, two extended field-generating structures positioned one on each side of the central payload region, symmetrically arranged to allow the warp geometry to form with the required energy distribution. The nacelle placement was not arbitrary and was not selected to resemble anything in particular. It was where the mathematics of the energy conditions pointed. Place the field-generating architecture in any other arrangement, and the energy conditions become harder to satisfy, the geometry becomes less stable, and the overall topology becomes less efficient by the metrics the team was optimizing against. The twin nacelle configuration was the answer the physical constraints produced when the team asked where the machinery had to go. The resulting design resembles the USS Enterprise, not approximately or superficially. The structural layout of twin nacelles flanking a central payload body, extending forward and positioned to allow a warp field to form symmetrically around the occupant region, is the same functional and visual configuration that the designers working for Gene Roddenberry described in 1966. Those designers had no knowledge of warp metric geometry. They were designing a fictional spacecraft to communicate the concept of fast travel through space. 31 years after Alcubierre wrote the equations that gave their imagined ship a mathematical basis, independent engineering constraints derived from those same equations reconstructed the ship's shape without anyone trying to reproduce it. White noted that the convergence between the physical requirements and the aesthetic of the fiction was not merely a visual coincidence, but a reflection of how the geometry of this class of warp topology naturally wants to be. Arranged, the equations and the imagination had arrived at the same place by entirely different roads. What that means for the questions still waiting at the edge of this science is something the next chapter of the physics has not yet answered. The coincidence of the nacelle geometry carries implications beyond aesthetics. The original television designers were solving a visual communication problem. How do you make a spacecraft look like it travels by manipulating space rather than by burning fuel? Their intuitive answer was to separate the propulsive machinery from the habitable body, to position it in flanking structures, suggesting a field rather than a thrust. The physics, working from first principles of energy distribution in a warp metric, arrived at the same configuration for entirely different reasons. When intuition and mathematics independently converge on the same answer, it raises the question of whether the intuition was drawing on something structurally real that formal physics later confirmed. There is a mathematical principle woven into general relativity that most descriptions of the warp drive concept quietly pass over, because the moment you state it plainly, the entire engineering project acquires a dimension that changes how it feels to think about. The principle is this: a ship inside a superluminal warp bubble cannot send any signal to the front edge of that bubble. The reason is geometrical. A bubble traveling faster than light develops a causal horizon at its leading surface, the same way a black hole develops a horizon at its boundary. Signals from the interior, traveling at the maximum permitted local speed, move toward the front of the bubble but fall behind the advancing edge faster than they can close the gap. The front wall is moving away from the interior faster than any signal from inside the bubble can pursue it. The engineering consequence of this confirmed theoretical fact is stark. The pilot of a superluminal warp drive cannot steer, cannot brake, cannot make any real-time decision about the trajectory, velocity, or destination of the bubble after it has achieved faster than light velocity. Any obstacle encountered in transit, a dense gas cloud, a gravitational gradient, another spacecraft, a planet, cannot be avoided using any control system located inside the bubble, because no signal from the control system can reach the front of the geometry in time to alter the path. The driver is sealed inside a box, moving faster than the fastest possible message the driver can send. The implication extends further than navigation. The occupants cannot communicate with the outside universe during transit. Any emergency arising inside the bubble cannot be communicated outward. Any external development affecting the destination cannot reach the occupants until after arrival. The warp bubble in operation is, by the physics of its own geometry, a closed system in a deep and consequential sense. You board it with a complete flight plan embedded before departure. You emerge at the destination according to that plan, having had no ability to modify any part of the journey based on information arising after the drive was engaged. This horizon problem has been present in the Alcubierre metric since 1994. Alcubierre noted it. Researchers who studied the metric subsequently noted it. No solution has emerged in the peer-reviewed literature. The difficulty is not a secondary engineering problem that will yield to cleverness about sensor placement or antenna geometry. It is a fundamental property of what the causal structure of superluminal spacetime geometry requires. The same equations that allow the effective faster-than-light traversal also preclude the internal steering that makes traversal safe to attempt. The two features are mathematically joined at their roots. Understanding how to build the drive and understanding that the drive cannot be controlled in flight may be the same discovery, and the field has not yet found a formulation that separates them. The horizon problem raises a question that the peer-reviewed literature addresses with striking honesty. Is the Alcubierre warp drive actually useful for crewed transport, or only for unmanned delivery of payloads requiring no in-flight adjustment? A robotic probe programmed before departure with a complete trajectory is not fundamentally limited by the horizon problem in the way a crewed vessel is. The probe has no pilot who needs to steer, no crew who needs to communicate during transit. Whether this limitation transforms warp drive from a technology for human exploration into a technology for sending pre-programmed packages to fixed destinations is a question that the engineering cannot answer. It depends on what humans ultimately want to do with it. The horizon problem tells you something about the front of the warp bubble. A second confirmed theoretical hazard concerns what accumulates there during the journey. A warp bubble moving through space is not moving through a perfect vacuum. Space at every scale is threaded with quantum vacuum fluctuations, virtual particles, and low-energy photons distributed through the cosmic microwave background radiation. As the front surface of the bubble advances, it encounters this material and sweeps it up. Under ordinary circumstances, the energy of this accumulated material would be modest and manageable. Under the conditions of a superluminal warp bubble, it is not. Particles swept up at the leading edge undergo a blue shift proportional to the bubble's velocity relative to the undisturbed space around it. Blue shift is the increase in frequency and energy that a wave or particle experiences when its source is approaching the observer. At velocities approaching and exceeding the speed of light, this blue shift becomes extreme. The energy of individual particles accumulated at the front surface of a warp bubble, traveling at significant fractions of light speed, or above it, would be scaled upward by factors that rapidly exceed the energies of the most powerful particle accelerators ever built. The leading edge of the bubble would concentrate this radiation and, upon deceleration or arrival at the destination, would release it. The release direction is forward. Ahead of the ship, everything in the path of the arriving vessel would encounter a pulse of radiation, scaled to the accumulated energy of every particle swept up during the voyage. Some calculations in the peer-reviewed literature suggest this pulse would be intense enough to destroy any planet or installation at the destination. This is theoretical, not confirmed by experiment, because no warp bubble has been built. But the physics driving the calculation is standard relativistic blue shift applied consistently to confirmed properties of the vacuum. There is no published resolution of this problem. The warp bubble in transit would, by the implications of the same framework that permits it to exist, be accumulating a weapon pointed at whatever awaits it. Whether the occupants inside would survive long enough to reach the destination, given the radiation environment building inside the bubble during transit, is a separate and also unresolved question in the technical literature. The blue shift catastrophe problem has a particular cruelty embedded in its structure. The warp bubble is designed to protect its occupants by creating an envelope of locally flat space-time around them. Inside the bubble, tidal forces are absent, acceleration is not felt, and the local laws of physics operate normally, but the protection is bounded. The front surface of the bubble interacts with the universe outside the protective envelope, and that interaction accumulates an energy concentration the bubble cannot contain. The safest internal environment imaginable is simultaneously producing the most hazardous event in the surrounding universe. The protection mechanism and the hazard mechanism are geometrically inseparable in every solution examined to date. A potential mitigation has been proposed in the theoretical literature, modifying the warp geometry so that the bubble decelerates gradually at the destination rather than collapsing rapidly, allowing the accumulated radiation to disperse in a direction away from the payload target. This is theoretical, and the energy mechanics of controlled deceleration in a superluminal bubble have not been fully worked out, but the problem at least has a proposed direction. Whether that direction leads anywhere physically realizable, or whether it simply transfers the hazard from the destination to the trajectory itself, is a question the field has not yet answered with any confidence. Nick Herbert was a credentialed physicist. He held a doctorate and had published in peer-reviewed journals. In 1981, he submitted a paper to a peer-reviewed journal describing a scheme he called the first laser-amplified superluminal hookup. The paper was accepted. The scheme proposed using laser amplification of quantum-entangled photon states to read those states precisely enough to compare with the partner particle instantaneously, extracting a faster-than-light communication channel from the apparent instantaneous correlation of entangled particle pairs. Herbert had identified a real phenomenon, the confirmed instantaneous correlation of quantum-entangled states across arbitrary distances, and designed what appeared to be a technically coherent method for using it to send information faster than light. The paper passed peer review. That fact embarrassed the journal, not because the editors had been careless, but because the flaw in Herbert's scheme was subtle enough to require a proof that had not yet been developed. Several physicists recognized that the scheme had to fail because it appeared to allow a violation of special relativity that no other experiment had achieved. The reason it had to fail was clear in outline. You cannot read the quantum state of an entangled particle with sufficient precision to extract information from it, because measuring the state disturbs it in a way that destroys the correlation you needed to measure. But stating this clearly as a proof required formalizing a constraint that physics had previously left implicit. William Wouters and Wojciech Zurek, working independently of each other, and Dennis Deeks, also working independently, all produced proofs in 1982. The proofs established what has since been known as the no-cloning theorem. An unknown quantum state cannot be perfectly duplicated. Herbert's scheme required copying an entangled photon state with perfect fidelity before measuring it. The no-cloning theorem proved this was impossible. The first laser-amplified superluminal hookup failed for a reason that had not existed as a formal result until the scheme forced physicists to articulate it. The no-cloning theorem is now one of the foundational results of quantum information theory and quantum cryptography. It underlies the security guarantees of quantum encryption schemes. It shapes the architecture of quantum computing research. A paper that was wrong, published by a journal that accepted it in error, forced the physics community to prove one of the field's most consequential modern theorems. The faster-than-light loophole that entanglement appeared to offer was genuine in its physical basis and genuine in its apparent implications. The mechanism that closed it advanced the science of quantum information by a generation. The universe declined to allow the shortcut, and in declining, produced something more valuable than the shortcut would have been. The no-cloning theorem has a relevance to quantum computing and cryptography that extends far beyond faster-than-light communication. The theorem establishes a fundamental limit on how quantum information can be copied, which determines the architecture of quantum computers and the security guarantees of quantum cryptographic protocols. Every quantum key distribution system operating today relies on it to guarantee that an eavesdropper cannot copy an intercepted quantum state without introducing detectable disturbances. The theorem that physics was forced to prove in order to close a loophole in special relativity ended up protecting modern quantum communications from precisely the kind of interception that classical cryptography cannot prevent. The universe closed one door and built a lock for every other door in the process. Alan Everett was examining the Alcubierre metric when he found something the original paper had not foregrounded. The warp drive metric, when you consider the sequence of events that multiple warp journeys could produce across different reference frames, creates the possibility of closed time-like curves. A closed time-like curve is a path through spacetime that returns to its own starting point in both position and time, allowing an object traveling that path to be present at the same location and moment it departed. The technical term carries a precise geometric meaning. In plain terms, it describes a time loop. This is a theoretical result derived from confirmed mathematics applied to a specific metric. Everett showed that two warp bubbles traveling on carefully chosen trajectories could, in combination, create the conditions for a traveler to arrive at a destination before the journey began, measured from an external reference frame. The mechanism does not require any violation of local physics inside either bubble. Both bubbles operate within their own geometries consistently. The time travel arises from the combined effect of the spacetime curvature the two journeys create when viewed from outside, in the global reference frame of the universe. This matters for reasons beyond the conceptual vertigo of time travel itself. The possibility of closed time-like curves creates what physicists call the chronology protection problem. Stephen Hawking proposed that quantum effects would destroy any spacetime configuration, attempting to become a closed time-like curve before it could close, through a mechanism involving the accumulation of infinite vacuum energy along the forming loop. This is theory, not confirmed experiment. Others have disputed Hawking's argument. The question of whether the universe permits closed time-like curves to form, and if so, what physical processes prevent or permit their operation, is unresolved in the peer-reviewed literature. What Everett's result means for warp drive research is that the question of faster-than-light travel cannot be fully separated from the question of time travel. They are the same physics. Every superluminal trajectory is, from some reference frame, a trajectory backward in time. A civilization with reliable warp technology would, by the structure of general relativity, have available to it the theoretical ingredients for time travel. Whether those ingredients can ever be assembled into a closed loop, whether the universe would permit that assembly, and what the consequences of such a loop would be for causality, are questions that the field cannot avoid and has not resolved. Hawking's chronology protection conjecture remains unconfirmed in the mathematical sense that physicists require. He argued from semi-classical gravity calculations that quantum fields would diverge as a closed time-like curve approached formation, producing infinite energy that would destroy the configuration before it could close. This argument has been challenged by researchers who found configurations where the divergence does not appear, or appears in forms that quantum gravity effects might regulate in ways current theory cannot calculate. The question of whether causality is self-protecting at the quantum level, or whether a sufficiently advanced civilization could assemble the ingredients for a time loop without the universe intervening, remains genuinely open and unresolved in the peer-reviewed literature. Sergei Krasnikov proposed a different approach to faster-than-light spacetime engineering, one that avoids some of the structural problems of the Alcubierre bubble by changing what the geometry is asked to do. Instead of creating a mobile region of modified spacetime that carries a payload from one location to another, Krasnikov described a fixed modification, a tube of altered spacetime stretching along a route between 2 points, within which the effective speed of light is higher than in the surrounding universe, allowing transit times shorter than light would need through ordinary space. This is theoretical, derived from valid mathematics within general relativity, published in the peer-reviewed literature. It carries an immediate and obvious problem that Krasnikov acknowledged fully. The tube cannot be built before the first journey. To create the tube, you must travel the route while depositing the geometric modification behind you. On the first trip, you travel through ordinary, unmodified space at ordinary speeds. The tube you create is useful only on the return journey and all subsequent transits. The person who builds the first Krasnikov tube between Earth and a distant star must travel there at subluminal speeds, which, given current technology, means the journey takes decades to centuries before the tube becomes available. The tube is not a shortcut to the stars. It is infrastructure that future generations could use, paid for in full in advance by whoever has the misfortune of making the first crossing. The question this raises is one the physics cannot answer, but the history of infrastructure suggests we should take seriously. Every piece of rapid transit infrastructure in human history was built by people who could not use it during construction for the benefit of people who would arrive afterward. The economic and civilizational motivation for building a Krasnikov tube is not obviously weaker than the motivation for building a transcontinental railroad or an ocean cable. The physics does not tell us who would build the first tube or what they would use to get there. The physics tells us that once the first tube exists, every civilization that follows has a faster road. Who builds the first road has always been the most consequential question in the history of travel. Krasnikov's proposal also illuminates something most faster-than-light discussions obscure: the difference between the physics of a warp mechanism and the logistics of using it. The Krasnikov tube and the Alcubierre bubble use related mathematical structures and face similar energy challenges. The operational difference is entirely in who pays and when. The first traveler pays the full subluminal travel cost in advance, across decades or centuries, in exchange for all subsequent transits through the corridor at superluminal effective speed. Whether that exchange is worth making requires answering questions about civilizational timescales and intergenerational infrastructure investment that physics cannot supply and economics can only partially address. The question of who builds the first Krasnikov tube also has an uncomfortable recursive quality. Any civilization capable of traveling at near light speed for decades or centuries to deposit a tube deserves to be asked how they survived the journey and what they used for propulsion during the tube construction phase. The answer, presumably, is some form of long-duration subluminal spacecraft far beyond current technology. In that sense, the Krasnikov tube presupposes a level of spacefaring capability that itself represents a substantial engineering achievement, making the tube less a solution to the problem of interstellar travel and more a force multiplier available to a civilization that has already largely solved it. The worst theoretical prediction in the history of physics is not a description chosen for dramatic effect. It is a phrase used in the peer-reviewed literature to describe a specific, quantified, the fully documented failure of the two most successful theories in the history of science to agree with each other about the single property they share. Quantum field theory, which governs the behavior of particles and forces at the smallest scales, predicts a value for the energy density of the vacuum. General relativity, which governs the geometry of spacetime and the behavior of gravity at the largest scales, observes a value for the energy density of the vacuum in the form of the cosmological constant, the parameter Einstein introduced and removed, and whose reinstated version we call dark energy. The two values differ by between 10 to the 50th and 10 to the 120th times, depending on which cutoff assumptions you apply to the quantum calculation. The discrepancy is not a measurement error. The discrepancy is too large by too many orders of magnitude to be an artifact of imprecise instruments. It is a symptom of genuine incompatibility between quantum mechanics and general relativity, the two theories on which all of modern physics depends, expressing themselves in contradictory terms about the most fundamental property of empty space. Understanding why this discrepancy exists and resolving it, is widely regarded as the most important open problem in theoretical physics. The resolution does not yet exist. The reason this matters for faster-than-light research is direct. Every warp drive proposal, every wormhole model, every theoretical framework for manipulating spacetime geometry as a vehicle for superluminal transport depends on understanding the quantum properties of the vacuum. The energy density of the vacuum is not background information that can be bracketed while the geometry is worked out separately. It is the medium the geometry operates in, and the resource it potentially draws from. A fundamental incompatibility in our understanding of what vacuum energy actually is sits at the center of the technical territory that every warp drive theory must cross. Until the cosmological constant problem is resolved, every proposal for vacuum-based spacetime engineering rests on a foundation that contains an undisclosed structural flaw. The cosmological constant problem also reveals something uncomfortable about scientific success. Quantum field theory and general relativity are each among the most precisely verified theories in the history of science. Quantum electrodynamics matches experiment to more than 10 significant figures. General relativity's predictions for gravitational wave frequencies and black hole merger dynamics have been confirmed with comparable precision. Each theory succeeds spectacularly within its own domain. When they are asked to agree on a single shared observable, the energy density of the vacuum, they disagree by between 50 and 120 orders of magnitude. Two perfectly accurate clocks that cannot agree on what time it is indicates not that one clock is wrong, but that they are measuring different things with the same name. The cosmological constant problem has resisted resolution for more than 20 years despite intensive work by the most technically capable researchers in theoretical physics. The standard approaches, attempting to find a symmetry principle that would cancel the vacuum energy contributions from different quantum fields, have consistently failed to produce a mechanism that works without introducing additional problems. This suggests the resolution may require a conceptual shift in how physicists understand the relationship between quantum fields and spacetime geometry, rather than a technical refinement of existing frameworks. The answer to this problem and the answer to the warp drive energy problem may ultimately come from the same place. In July of 2024, Andrzej Dragan from the University of Warsaw and Artur Eckert from Oxford published a paper in Physical Review D. The subject was Tachyons, the hypothetical particles that always travel faster than light, named by Gerald Feinberg in 1967. The tachyon had occupied a consistent position in physics for nearly 6 decades. Mathematically describable, never detected, theoretically problematic because of its implications for causality, and categorized in the mainstream literature as a mathematical curiosity rather than a physical candidate. The specific technical objection most frequently cited was that tachyon fields appeared to violate causality when coupled to ordinary matter, potentially enabling messages to arrive before they were sent. Dragan and Eckert argued in their peer-reviewed paper that this objection was based on an incorrectly applied set of boundary conditions. The boundary conditions in question had been introduced in the original mathematical treatment of tachyon fields and had been carried forward into subsequent analyses without being rigorously re-examined. When the boundary conditions were applied correctly, Dragan and Eckert argued, the causality violations that had been used to exclude tachyons from serious physical consideration no longer arose. The mathematical door that the physics community had considered firmly closed for 60 years had, by their argument, never been properly latched. This is the status of the result, peer-reviewed, published in one of the central journals of physics, not yet accepted as consensus, not retracted, actively being evaluated by researchers in the relevant areas of theory. The authors are credentialed physicists at leading institutions. The argument is technical and specific. The claims it makes about the correctness of previous boundary conditions have not been independently confirmed as of the research available through early 2026. What can be stated accurately is that the question is open in a way that the previous 30 years of physics had not acknowledged as open. One of the most enduring categorical exclusions in the field has been placed formally in dispute by researchers who did the full mathematical work in a venue where such disputes are supposed to be resolved. Whether tachyons can exist is now a genuinely contested scientific question rather than a settled one. 60 years of apparent closure may have rested on a calculation error. The consequences of that possibility are still being worked out. The consequences of reopening the tachyon question extend beyond the particles themselves. If tachyons can exist without causing the causality violations that previous analyses predicted, the question of what other closed questions in faster-than-light physics might have rested on similarly unchallenged assumptions becomes impossible to ignore. Boundary condition errors are a recurring failure mode in theoretical physics. They arise when a calculation is performed with assumptions about what is permitted at the edges of the mathematical domain, and those assumptions are carried forward without being independently verified. The Dragon-Eckert paper is not a demonstration that tachyons exist. It is a demonstration that the strongest argument for their impossibility contained an error that went unexamined for 60 years. Juan Maldacena and Leonard Susskind published their conjecture in 2013. The paper proposed that two apparently separate phenomena, both fundamental to modern physics, might be the same phenomenon viewed from different scales. The first is quantum entanglement, the confirmed experimental fact that two particles, once entangled, maintain instantaneous correlations regardless of the distance between them. The second is the Einstein-Rosen bridge, the geometric construct, also called a wormhole, that appears as a solution to the field equations of general relativity and describes a tunnel connecting two separate regions of spacetime. Maldacena and Susskind proposed that these are not two different things. They are the same structure. Every pair of entangled particles, the conjecture holds, is connected by a microscopic wormhole through the geometry of spacetime. The instantaneous correlation observed in entanglement experiments is not a mysterious action at a distance. It is a geometric fact. The two particles are connected through a spacetime bridge too small for any current instrument to resolve, and what appears to be non-local correlation is actually local geometry at a scale we have not yet learned to measure. The conjecture is taken seriously in theoretical physics. It has not been proven. It has not been falsified. It has been explored extensively in the research literature, particularly in the context of holographic models of gravity that use similar mathematical frameworks. If the conjecture is correct, the implications for faster-than-light research shift the question from engineering to fundamental physics in a specific way. Every entanglement experiment ever performed has been, unknowingly, creating and manipulating microscale wormholes. The geometry of spacetime that warp-drive theorists are working to create at macroscopic scales may already be present, in miniature, in the quantum correlations of ordinary particles. The universe may have been threading spacetime with wormhole connections all along, at a scale invisible to all our instruments, in every laboratory and in every piece of matter everywhere. What prevents us from using that geometry is not its absence. It is our inability to address it at the scale where it currently lives. The ER equals EPR conjecture, if correct, would not immediately provide a mechanism for faster-than-light communication. The wormholes connecting entangled particles are, in Maldacena and Suskind's framework, non-traversable. A signal cannot pass through them any more than information can be extracted from entanglement correlations. The conjecture reframes the why of entanglement without changing the what. But it opens a question that the non-geometric interpretation leaves closed. If the wormhole connection between entangled particles is a physical geometric feature of spacetime, rather than an abstract mathematical relation, then understanding what happens to that geometry when entanglement is broken may eventually suggest handles on spacetime topology that the purely algebraic description conceals entirely. What makes the ER equals EPR conjecture particularly relevant to warp drive research is its implication about the ubiquity of wormhole geometry in nature. If every entangled particle pair is connected by a microscopic wormhole, then wormhole topology is not a rare or extreme condition requiring exotic matter to create. It is the default state of entangled matter throughout the universe. The exotic matter requirement for traversable macroscopic wormholes might then be understood not as a requirement to create wormhole geometry where none exists, but as a requirement to amplify and stabilize geometry that already permeates the quantum substrate of spacetime. Whether that reframing changes the energy calculations is a question that the research programs now operating on the boundary between quantum information and general relativity are beginning to address. The nearest term milestones are not starships. They are not even prototype drives. They are energy reductions, measured in orders of magnitude, achieved against a baseline gap that currently stands at 52. Lentz himself stated in his published work that 30 orders of magnitude reduction would be required before the energy costs of a warp drive could be considered within range of what a highly advanced civilization might plausibly concentrate for a single purpose. 22 additional orders would still remain after that. The path toward those reductions runs through several research frontiers that currently have active programs but no confirmed breakthrough. Understanding dark energy well enough to work with its underlying physics is one of them. Dark energy is the universe's own mechanism for sustained faster-than-light space-time expansion, operating continuously across cosmic scales. We have measured it, confirmed it exists, determined its approximate magnitude, and acknowledged that our best theoretical frameworks disagree with the observed value by between 50 and 120 orders of magnitude. If dark energy is a dynamic field rather than a fixed cosmological constant, it changes over time and potentially over position. If it changes over position, in principle, it could be engineered locally. These are theoretical possibilities, not engineering programs, but the science of identifying which possibility is physically correct and what the implications would be is a legitimate ongoing research question. The soliton warp drives of the Lentz class need to be understood well enough to know whether the energy cost can be reduced through geometric refinement or whether the current figures represent a lower bound for that class of solutions. The open-source Warp Factory software, released in 2024, is now enabling researchers around the world to test variants systematically. The Casimir cavity work that accidentally produced the warp geometry match is continuing as an active experimental program. The quantum vacuum, at microscopic scales, is demonstrably producing energy density geometries that match theoretical warp metrics. What that match means at larger scales, and whether it points toward a physical mechanism that could be amplified and directed, is a question with an experimental path rather than just a theoretical one. The science has moved, in the course of the last 5 years, from categorical impossibility to an engineering problem with an enormous but finite gap, a growing set of mathematical tools, and a distributed global research community for the first time using shared computational infrastructure. In physics history, the transition from impossible to impossibly hard has a specific track record. The atom was indivisible until it was split. The sound barrier was an absolute limit until it was crossed. The pace at which the hard problems yield depends on whether the right framework has been found, whether the energy gap reflects the fundamental structure of what is being attempted or a failure of imagination in how it is being approached, and whether any of the frontiers currently being explored contain a discontinuity that changes everything. None of those conditions can be evaluated from where we currently stand. What can be said is that the research is real, the peer review is legitimate, and the direction has been established. The distance is the question. We do not know whether the universe will allow what we are trying to build. That is the most accurate single sentence describing the state of faster-than-light research as of the middle of this decade, and every technical detail accumulated across this investigation leads back to it. The math permits a warp bubble. General relativity does not prohibit it. The papers published in March 2021 established that exotic matter is not a required ingredient. The equations allow a vessel to leave Earth and arrive at a distant star in days, weeks, or hours, carried by the curvature of geometry, rather than pushed by any engine through stationary space. These are confirmed theoretical results in the peer-reviewed literature, produced by credentialed researchers at legitimate institutions, published in the relevant journals, surviving scrutiny and being built upon by subsequent work. And beneath all of it, unresolved, the deeper questions wait. If the bubble forms, it creates a causal horizon. The pilot cannot steer, the radiation ahead cannot be warned. Everything in the path of the arriving vessel will encounter the energy accumulated at the leading edge during transit. Some calculations suggest this pulse would destroy whatever waits at the destination. Nobody has published a solution. If the vessel completes multiple journeys, the geometry of the trajectories may create closed, time-like curves. A warp drive is a time machine in the mathematics that describes it, and the question of whether the universe would allow the loop to close, whether quantum effects would destroy the configuration before causality could be violated, is one of the central unsolved problems in theoretical physics. Tachyons may have existed in the early universe, before the Higgs field settled to its current value. If the 2024 Warsaw-Oxford paper is correct that the causality objections against tachyons rested on a 60-year-old mathematical error, then faster-than-light particles could theoretically exist, and could theoretically carry information backward in time from some reference frames. The connection between entangled particles may be a wormhole too small to see. The energy of the vacuum, which any warp drive must engage and manipulate, is something our best theories cannot agree on by 50 orders of magnitude. We have learned, in the 31 years since a graduate student watching television wrote a metric that changed the conversation, that the universe's speed limit is more nuanced than it first appeared. Spacetime moves where matter cannot. The loophole is real. The work to use it has barely begun. What we have not learned, and what the next decades of physics must confront, is whether the act of using the loophole would come at a cost embedded in the structure of causality itself, a cost the universe may have ways of collecting that we have not yet imagined. The door that relativity left open may open onto something far stranger than the stars on the other side. We are still standing at the threshold, reading the equations by the light of everything we know, unable to see clearly what lies beyond them, and that uncertainty is the most honest thing physics can offer about where we are headed.